So oscillations in stars are sound waves inside the star bouncing around. A star is a hot ball of gas and it is shaken by the convection in the outer part of the star, and that causes it to vibrate and oscillate. I can give you an analogy. I have this tube here. When I swing it around, you can hear a sound. Now if I swing it harder, you can hear a different sound. So all of these sounds are oscillations inside the star. Each one of them has a different frequency. And the analogy with stars, if we measure the different frequencies of the oscillations, we can tell about the insides of the stars. We've learned a lot about the sun from the oscillations in the sun, and so the natural next step is to look at stars that are like the sun. So we call these solar-like stars. Stars like the sun also have convection in the outer parts, and they're also shaking. With the Kepler satellite, we're able to observe oscillations in these stars as well. They're similar to the sun, but slightly different, and it's the differences that are important. For example, we can look at stars a little bit older than the sun or a bit more massive than the sun and see what the differences are. For red giants, these are what the sun will become when it's older. It will expand and become much bigger, many times bigger, but it will still be oscillating, but with a lower frequency, a lower note. By measuring these oscillations, we can tell what's inside these red giants, how dense they are and what they're made of. One of the exciting things about astroseismology is that we can learn about the stars that have planets around them. We're learning more and more stars have planets, solar systems, some like our own. We would like to know about the stars in the middle of those solar systems and, for example, how hot they are, how old they are. We can do this by astroseismology. The oscillations in the stars, we can measure them and we can use this to determine the sizes of the stars, the ages of the stars. So the next generation of extremely large telescopes are very exciting for astronomy. There's a possibility that 2 or even 3 of these will be built in the next decades. The question of where to put them is an interesting one. Of course, we want to choose the best sites, the ones with the best weather, the clearest skies and the best seeing. That is, the images are very stable. But of course, it would also be nice to have one telescope in each hemisphere, one in the north and one in the south, so that we would have access to the whole sky. So of course it's very busy combining teaching and research at a university, but I think it's very rewarding also for the students, because they have lectures then from researchers who are active in the field and can be telling them things about new research as it's happening. Of course it takes a lot of time to do teaching, it takes away some of the time for research, but it's very valuable. Also it gives us access to students, because the students can be doing research projects with us and maybe also going on to a PhD. So in Australia, the students come to university from high school and they start studying physics and mathematics straight away. Over the years, we maybe notice a little bit of change in students, but I think not so much. In the end, we get very good students at the university, and most of them have done the physics and mathematics in high school. The high school syllabus does change with time, but I think it's fair to say that the quality of students now is just the same as it was many years ago.